In this video, I'm going to show you how to compute definite integrals of power functions using the fundamental theorem of calculus. So first of all, let's talk about that fundamental theorem of calculus. The fundamental theorem of calculus states, first of all, given a function f that is integrable on this interval ab. Actually, before we go on, let's stop right there and clarify what we mean by integrable. By integrable, we just basically mean that the function f is continuous and smooth on its domain a to b. Now, this theorem actually does work for some non-smooth and even some non-continuous functions f, but for now we can just think of f as being continuous and smooth over its domain. We'll worry about the other types of functions later. Okay, so now that we've clarified what f is an integrable function on the interval from a to b. Suppose we have another function, capital F, such that the derivative of capital F is lowercase f on this interval a to b. So in other words, capital F, is really just an antiderivative for f. So suppose we have that integrable function, lowercase f, along with an antiderivative, uppercase f, on this interval a to b, then the fundamental theorem of calculus says that we have that the integral of lowercase f, so integral of f of x dx, a definite integral from a to b, so the definite integral of lowercase f of x dx on a to b is equal to the antiderivative, capital F, evaluated at the top bound, b, minus that same antiderivative, capital F, evaluated at the lower bound, a. Now, this is a really, really useful and important theorem. And the reason it's so useful and important is that it gives us a faster way to compute integrals than taking Riemann sums like we're used to doing. We just need to find the antiderivative of the function within the integral, and then we evaluate it at the bounds of the integral, and then subtract, and then we're done. Alright, now let's put this fundamental theorem of calculus to use on an example. Say we want to compute the integral of x squared dx from 0 to 1. In the fundamental theorem of calculus, the inside of that integral is f of x. So in this case, x squared is f of x. So let's just write that down here. F of x equals x squared. Now, capital F, that is the antiderivative of f of x. So let's write that down. Capital F of x is the antiderivative of f of x, so antiderivative of x squared dx, and we know how to compute that antiderivative using the power rule. That's just the exponent increases to 3 and then divide by 3. So 1/3 x cubed, then plus some arbitrary constant. So now let's write down that statement of the fundamental theorem for this integral in particular. For this integral in particular, we have the integral from 0 to 1 of small f of x, which is x squared dx, is equal to capital F of x, that antiderivative, so 1/3 x cubed plus constant, evaluated at the bounds. So we're going to draw a vertical line here and put the bounds 0, 1, and that just means to plug in 1 into this function, evaluate it. That'll give us like f of b, this function evaluated at 1, and then plug in 0 to the function and evaluate that and then subtract. That's just a compact notation of writing it when we've got an actual function expression here. So let's go ahead and write that. That's equal to, let's plug in 1 first. So 1/3 times 1 cubed plus our constant of integration, and then minus the same thing, but now we plug in 0. So 1/3 times 0 cubed plus our constant of integration, and now we just have to go ahead and compute this. Okay, so this comes out to 1/3. 1 cubed is just 1, so this is just 1/3 plus c, and then minus put in parentheses, 0 cubed is just 0. So this is 1/3 times 0, which is just 0. And then plus our constant. So let's go ahead and simplify this. This is 1/3 plus the constant, then minus the constant. The constant just cancels, and then we just have 1/3. So there we go. That is the result of our integral. Now, looking back, one thing to notice is that the constant of integration canceled here. And that'll happen all the time, no matter what the function is. Its antiderivative will be some expression of x, then plus a constant, and then the constant will just cancel at the end. So for that reason, we usually don't write the constant of integration when we find the antiderivative. We just leave it out, and it comes out to the same result anyway because it would cancel. So that's what we'll do going forward. We won't bother writing the plus c when we're dealing with definite integrals. Alright, here's another example. Again, we want to use the fundamental theorem of calculus to compute another integral. This time it's the integral of root x dx from 4 to 9. So let's go ahead and write that down in our colors. So we want to calculate the integral. Its bounds are at 4 and 9. The function small f of x inside the integral is root x, and then we've got our dx, and we know that's going to be equal to the antiderivative evaluated at the bounds and then subtracted. So first, let's go ahead and compute our antiderivative. And to do that, why don't we express the inside of this integral a little bit differently? So let's write it again, but let's write it instead of a root, let's use an exponent. That way we'll just be able to apply the power rule. So instead of root x, we'll write x to the 1/2, and then dx. Okay, and now let's go ahead and evaluate. That's a lot easier to take the antiderivative of. All we have to do is increase the exponent by 1, so x to the 3/2, and then multiply by the reciprocal, so 2/3, and then that's our antiderivative, and we need to evaluate that at the bounds. So draw a vertical line, put our bounds 4 and 9, and now it's up to us to go ahead and compute it. So we'll stick in that upper bound first, 9, so 2/3 times 9 to the 3/2, and then minus 2/3 times that lower bound, 4 to the 3/2. Alright, now let's just go ahead and compute. So that's 2/3. Why don't we write this as 9 to the 1/2 and then that to the 3rd, just so it's easier to compute. Same with the other one. 2/3, take 4 to the 1/2 and then to the 3rd, because now we can just do 9 to the 1/2 is just root 9, which is just 3. So 2/3 times 3 to the 3rd minus 2/3 times root of 4 is just 2, so 2 to the 3rd. So then that's 2/3 times 27 minus 2/3 times 8, and then we just multiply through. We get this is 54/3, and then minus 16/3, which comes out to just 38/3. So there we go. There is our final result for the integral. Here's a final example using the fundamental theorem of calculus again. This time we want to compute the integral of 1/x² dx from x is 2 to x is 3. Alright, so let's go ahead and write this nice and using color with our fundamental theorem. So integral, the bounds are at 2 and 3. Our inside function, small f of x, that's just 1/x², and we're taking that integral with respect to x. Okay, so what is that equal to? We want to find an antiderivative of this expression inside the integral, and in order to do that, it's going to be a lot easier if we write this as just x raised to some power instead of a fraction. So why don't we write this, instead of 1/x², let's write it as x to the power of -2. Okay, so put in our dx, and now that's a lot easier to take the integral of, so that's just equal to taking the antiderivative of this. We just have to increase the exponent by 1, so x to the negative 2 plus 1 makes just negative 1, and then multiply by the reciprocal, so 1 over negative 1, and that's evaluated at the bounds 2 and 3. So now we just have to go ahead and plug those in. Before we plug them in, why don't we just simplify this a bit? This reciprocal 1 over negative 1, that's just a negative. So negative x to the negative 1 evaluated at the bounds 2 and 3. Why don't we even write this, instead of x to the negative 1, why don't we write this as 1 over x? And that'll still be at the bounds 2 and 3. Okay, now it looks pretty easy to plug in and compute, so let's go ahead and do that. So plugging in our top bound, it's negative 1 over top bound is 3, and then minus negative 1 over bottom bound is 2. Okay, so simplifying this then, we just have negative 1/3. The negatives cancel here, so plus 1/2. Why don't we add these fractions, so convert them to common denominator. How about over 6? So multiply by 2 on top and bottom here, so negative 2/6, and then plus multiply by 3 on top and bottom here, so plus 3/6, and then negative 2 plus 3 just makes 1, so 1/6. There we go. That's the result of our integral. So now we know how to use the fundamental theorem of calculus to quickly compute definite integrals of power functions. In the future, we'll see how to apply the fundamental theorem of calculus to other functions, including discontinuous piecewise functions.